The Pantheon has been standing in Rome for almost 1900 years. Its dome, made of concrete, is the largest unreinforced concrete dome ever built. No steel bars inside, no modern engineering tricks, no rebar, no tension cables, no post-tensioning, just concrete, and it is still there, still holding, still perfect. You can go stand under it right now and look up, and you will see the same dome that Roman citizens looked up at when it was dedicated in the year 128. Meanwhile, drive across any American highway built in the 1960s. Cracks everywhere, rebar poking through like broken bones through skin, chunks falling off bridges that are barely 50 years old. We spend billions of dollars a year patching concrete that was supposed to last a century and barely made it past a generation. So here is the puzzle that is going to keep us busy today. The Romans built concrete structures 2,000 years ago that are still getting stronger. Our concrete starts falling apart after a few decades. Same basic material, calcium, rocks, water. They had no chemistry textbooks, no electron microscopes, no computers, no understanding of molecular bonds or crystallography. We have all of those things, and our concrete is worse. Something is very wrong with this picture, and I want to figure out what. Let me start where I always start, with the atoms. Because when you do not understand something, you have got to go down, down, down until you can see what the atoms are doing. Everything else is just storytelling, until you know that I have said this 1,000 times, and I will say it 1,000 more. If you want to understand anything, you have to ask, what are the atoms doing? So what is concrete? Strip away all the engineering language and the construction industry jargon, and at the most basic level, concrete is a glue holding rocks together. You take some rocks, some sand, some gravel, little pieces and big pieces, and you mix them with a paste that starts out wet and becomes hard. The rocks are the filler. They provide bulk and strength and shape. But the paste is the interesting part. The paste is where the action is. In modern concrete, that paste is made from something called Portland cement. Here is how you make it. You take limestone, which is mostly calcium carbonate. If you remember your chemistry, that is one calcium atom bonded to one carbon atom bonded to 3 oxygen atoms, all stacked together in a crystal that you would recognize as chalk, or seashells, or the white cliffs of Dover. You take that limestone, you mix in some clay for the silica and alumina, and you heat the whole thing in a rotating kiln to about 1400 degrees Celsius. That is hot enough to glow bright orange, hot enough to melt copper. At that temperature, the calcium carbonate breaks apart. The carbon dioxide molecule lets go and flies away as gas. What stays behind is a collection of new compounds, calcium silicates and calcium aluminates mostly, fused together into lumpy gray nodules called clenite. You grind those nodules into a fine powder. That powder is Portland cement. Now you add water, and something wonderful happens. The calcium silicates reach out and grab onto the water molecules. Not gently. They react, rearrange, form entirely new crystal structures, little needles and plates and sheets that interlock and bind everything together like microscopic fingers gripping each other. Imagine pouring water onto a tray of dry spaghetti, and the spaghetti instantly weaves itself into a fabric. That is roughly what happens at the nanometer scale when water meets Portland cement. These needle-like crystals, called calcium silicate hydrate, are the real glue. They grow outward from each cement grain, reaching toward the crystals growing from neighboring grains, until eventually they all interlock into one continuous rigid mesh. This process is called hydration. It is exothermic, meaning the atoms give off energy as they rearrange. If you have ever touched fresh concrete and felt it warm to the touch, that is not the sun heating it. That is the chemical reaction happening right under your hand. Atoms finding their partners and settling into their new arrangement, releasing a little burst of energy with each new bond. In a big pour like a dam foundation, the heat can be a real problem. It can actually crack the concrete from within if you are not careful about managing it. And here is the key thing about Portland cement concrete. Once those crystal structures form, that is essentially it. The reaction is done. Oh sure, concrete keeps curing for weeks, even months. The construction industry tells you to keep it moist for 28 days. Deep inside a thick pore, water molecules are still slowly diffusing through, finding their way to pockets of unreacted cement. But fundamentally, the architecture is set. The crystal lattice is built. It has found its final configuration. And it is not going to change. And here is the problem with any rigid crystal lattice. If you crack it, it stays cracked. Think of it like a window. Glass is a beautiful, strong, transparent material. Harder than you might expect. But the moment you put a crack in it, that crack is permanent. The atoms on either side of the fracture are locked in place. They have no mechanism, no chemical pathway, no instructions to move across the gap and knit themselves back together. Glass does not heal, and neither does Portland cement. The chemistry is finished. The atoms have done all the rearranging they are going to do. When a crack forms in modern concrete, it is an open wound that never closes. Water gets in. It carries dissolved salts and acids. It reaches the steel reinforcing bars buried inside, and those bars begin to rust. Rust takes up more volume than the original steel, so as the rebar corrodes, it swells, pushing outward, creating more cracks from the inside. Meanwhile, winter comes. The water in the cracks freezes, and water does something unusual when it freezes. It expands, about 9% by volume. That expansion pushes the crack wider. Spring arrives, the ice melts, more water flows in, filling the now larger crack. Next winter, it freezes again, wider still. This is called frost wedging, and it is relentless. Year after year, the cracks grow, branching and spreading like the roots of a tree through the material. Eventually, the rebar rusts, the surface spalls, and the highway department comes out with jackhammers and orange cones and a budget overrun. This is why highways fall apart. It is not that the concrete was bad when it was poured. It is that concrete has no immune system. It cannot respond to damage. It is a dead material. Chemically speaking, once set, it just sits there, waiting to be broken. All right. That is our modern situation. What were the Romans doing differently? For a long time, the standard answer was volcanic ash. The Romans used a material called pozzolana, named after the town of Pozzoli on the Bay of Naples, right there in the shadow of Vesuvius. This volcanic ash is special. When a volcano erupts, the explosion shatters minerals into tiny fragments with enormous surface area, and those fragments are chemically hungry. They are full of silica and alumina in a disordered reactive state. When you mix this volcanic ash with lime and water, the silica and alumina attack the calcium hydroxide and form extremely strong, extremely stable compounds. Calcium silicate hydrate and calcium aluminate hydrate. Tight, interlocking crystals that resist water, resist stress, resist time. The Romans shipped this ash all across their empire. They recognized it was something special. A Roman architect named Vitruvius wrote about it around 25 years before the Common Era, describing how to mix it and what proportions to use. So the standard story for decades was, the Romans had great volcanic ash. They mixed it with lime, they got great concrete, mystery solved. But that cannot be the whole story, and you should be suspicious whenever someone tells you a mystery is solved by a single ingredient. Nature is rarely that simple. Here is why the volcanic ash explanation falls short. Not all Roman concrete survived. Some of it crumbled just like ours. The ash was used across the empire, but the results varied wildly. Concrete at one site lasted 2,000 years. Concrete at another site using similar ash did not. If the ash were the whole secret, you would expect consistent results wherever the ash was used. You do not get that. Something else is going on. And here is the clue that kept nagging at researchers. Firm, in the really durable Roman concrete, the stuff that survived earthquakes and centuries of rain, and even constant battering by ocean waves, they kept finding these little white chunks, millimeter-scale lumps of calcium, scattered through the matrix like raisins in a cake. You could see them with the naked eye if you broke open a sample, little white spots in a gray background. There is an ancient tomb on the Via Appia, the famous Roman road leading south out of Rome. It is called the tomb of Cassilia Metella, built around 30 years before the Common Era for the daughter-in-law of a wealthy Roman general. The tomb is a massive cylinder of concrete, about 11 meters in diameter, and it has been sitting exposed to the Italian weather for over 2,000 years. When researchers examined its concrete, they found those same white lime clasts, but they found something else too. They found that cracks in the concrete had been filled with calcite crystals. New mineral growth formed long after the original construction, filling fractures that had opened up over the centuries. The tomb was healing itself. Right there on the road out of Rome, the evidence was staring everyone in the face. For decades, the scientific community looked at those white lumps and collectively shrugged. Poor quality control, they said. The Romans did not stir their concrete well enough. Some lime failed to dissolve. Manufacturing defects. Nothing to see here. Move along. That explanation always bothered a chemist at MIT named Admir Masick, because the Romans were not sloppy builders. They constructed aqueducts that carried water across hundreds of miles using gravity alone, with a grade so precise that some of them still deliver water to Rome today. They built harbors in the open sea. They paved 50,000 miles of roads. These were not people who forgot to stir the pot. There had to be another explanation. So Masick and his team gathered samples of 2,000-year-old concrete from the ruins of Privenum, an ancient site south of Rome. They brought the samples back to the lab at MIT and aimed every tool they had at those little white lumps. Scanning electron microscopes, energy dispersive X-ray spectroscopy, powder X-ray diffraction, confocal Raman imaging. They mapped the chemical composition of those lumps atom by atom, and what they found changed the story completely. Those lumps are something called lime clasts, and they are not a mistake, they are the whole secret. To understand what a lime clast is, you have to understand two forms of lime, and the difference between them matters enormously. When you heat limestone in a kiln, you drive off the carbon dioxide and you get calcium oxide. Pure, white, caustic calcium oxide, that is called quicklime, and it is ferociously reactive. If you splash water on quicklime, it does not just dissolve politely, it hisses, it steams, it gets so hot it can boil the water right off. The reaction releases about 65 kilojoules per mole. For comparison, that is enough energy that a large pile of quicklime with water poured on it can actually catch nearby materials on fire. The medieval English Navy reportedly used quicklime as a weapon, throwing it at enemy ships to blind the crews. Now, the assumption for years was that the Romans were careful. They would take the quicklime and slowly add water to turn it into calcium hydroxide, which is called slaked lime. Slaked lime is tame, gentle, a smooth white paste, easy to work with, easy to mix. The thinking was the Romans made slaked lime first, then combined it with volcanic ash and aggregate to make concrete. But Masick's team found evidence of something much more violent. The chemical signatures in those lime clasts showed that the Romans were mixing quicklime directly into the concrete while it was still in its raw, wildly reactive form. They were not taming the quicklime first, they were throwing it in hot. This technique is called hot mixing. You take dry quicklime, volcanic ash, water, and aggregate, and you combine them together. The quicklime reacts with the water violently, the temperature spikes. The whole mixture gets blazing hot, possibly locally reaching temperatures of several hundred degrees. That extreme heat accelerates and alters the chemical reactions happening in the mix. It creates bonds and structures that a calm, room temperature process would never produce. And here is something beautiful. And in the ruins of Pompeii, buried under volcanic ash since the year 79 when Vesuvius erupted, archaeologists recently uncovered an actual Roman construction site frozen in time. There were piles of raw material still sitting there, sorted and organized, piles of volcanic tuff blocks, piles of pre-mixed dry ingredients. The whole workspace abandoned in the middle of a job almost 2,000 years ago. Researchers from MIT analyzed these materials and found clear evidence that the builders were preparing for hot mixing. The dry quicklime and volcanic ash were staged for combination, not pre-slaked. This was not some regional quirk or one builder's experiment. This was standard practice, at least at this site, preserved by the very volcano, that supplied their raw materials. The irony is almost too perfect. But back to the chemistry. During hot mixing, not all of the quicklime fully reacts. Some lumps get their outer surfaces coated in reaction products before the water can penetrate to their cores. The reaction is so fast and so violent on the surface that it creates a kind of shell, sealing the interior. These partially reacted chunks get locked into the concrete matrix as lime clasts, little time capsules of reactive calcium sealed inside the hardened material, dormant but chemically ready. 2,000 years later, those lime clasts are still in there, still chemically potent, still waiting for their moment. And here is where the story becomes extraordinary. Imagine the concrete is like your body, and the lime clasts are like little capsules of medicine stored under your skin. As long as everything is fine, they sit there quietly. They do not react, they do not interfere. But the moment a crack forms, everything changes. When a crack develops, water seeps in through it. This is the same water that destroys modern concrete. The same water that freezes and expands and tears the material apart year after year. But in Roman concrete, the water reaches a lime clast, and it triggers a chemical response. The calcium oxide at the core of the clast dissolves into the water, creating a solution rich in calcium. That calcium-saturated solution flows along the crack, filling it. Then, as it encounters carbon dioxide from the air, or as it simply dries out, the dissolved calcium precipitates as calcium carbonate. New mineral crystals growing right there in the crack, filling it, sealing it, gluing the two sides back together. The crack heals itself, the concrete repairs its own wound. Masik's team tested this in the lab. They manufactured concrete using the Roman hot mixing method, let it cure and harden, then deliberately cracked each sample, cracks about 0.5 millimeter wide. Then they ran water through the cracks. Within 2 weeks, the cracks in the hot mix samples had completely sealed. No more water could pass through. They tested identical concrete made without the lime class as a control, cracked it the same way, ran water through, and the cracks stayed wide open. The water flowed through forever. No healing, no repair, just a dead material with a permanent wound. 2 weeks. That is all it took. The modern concrete never healed at all. The Roman-style concrete sealed cracks up to about 0.6 millimeters across. For comparison, modern self-healing concrete technologies, using expensive embedded capsules of epoxy or engineered bacteria, can only manage cracks of about 0.2 or 0.3 millimeters. The Roman method, using nothing but lime and volcanic ash and heat, outperformed them all. And it costs almost nothing extra. You just have to be willing to let the mixing get hot and messy. And this mechanism does not just work once. Every time a new crack forms and water enters, it can trigger the same response as long as there are lime clasts nearby. And those clasts are distributed throughout the entire matrix, scattered everywhere, like a distributed immune system. The concrete has thousands and thousands of these little repair stations built in. It can heal itself over and over again for centuries, for millennia. Each healing event uses up a tiny amount of calcium from one clast, but there are so many of them that the supply lasts for an extraordinarily long time. The concrete is not just strong, it is responsive. It has a built-in chemical repair system operating at the atomic level. Every crack triggers its own remedy. And all of it happens without any intervention, without any engineer, without anyone even noticing. Just atoms following the rules of attraction and repulsion. I once said if all of scientific knowledge were to be destroyed and only one sentence could be passed on to the next generation, the best sentence would be this: all things are made of atoms. Little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence there is an enormous amount of information about the world, if just a little imagination and thinking are applied. Roman concrete is a perfect illustration of that principle. The calcium atoms in those lime clasts are attracted to the oxygen in water molecules. When water enters a crack, that attraction pulls the calcium into solution. Then the calcium encounters carbon dioxide, and the attraction between calcium, carbon, and oxygen pulls them into a new arrangement, calcium carbonate crystals. No engineer planned this response on a crack-by-crack basis. No one dispatches a repair crew into the concrete. The atoms do it themselves, because the laws of physics leave them no choice. Given the right arrangement of materials, self-healing is not just possible, it is inevitable. Now let me push deeper, because there is yet another layer to this mystery, and it involves the ocean. Some of the most impressive Roman concrete is found in marine structures, harbor walls, and breakwaters that have been sitting in salt water for 2,000 years. Seawater is devastating to modern Portland cement concrete. The salts corrode the rebar, the magnesium and sulfate ions attack the cement paste, and within decades the structure is falling apart. We spend fortunes trying to protect modern marine concrete from the ocean, but Roman marine concrete actually benefits from seawater exposure. Researchers found that over centuries the minerals in the volcanic ash react slowly with the seawater to form an extremely rare and extremely strong crystal called aluminous tobermarite. This crystal is nearly impossible to synthesize in a laboratory. It normally requires very high temperatures and specific pressures. But in Roman marine concrete it grows naturally, slowly, grain by grain, as seawater seeps through the material over hundreds of years. Tobermarite reinforces the concrete from within. It fills pores and strengthens the binding matrix. So Roman marine concrete is not just healing its cracks with calcium carbonate. It is growing entirely new reinforcing crystals inside itself using the very seawater that would annihilate modern concrete. The thing that destroys our material feeds theirs. The ocean, which is the enemy of Portland cement, is the ally of Roman concrete. Stop and think about that for a moment, because it is one of those facts that rearranges how you see things. We design our marine concrete to resist the ocean. We coat it, we seal it, we fight the water with every tool we have, and we lose. The Romans designed a material that cooperates with the ocean, that uses the water as a delivery system for new mineral growth. They did not fight nature, they built something that works with it. Whether they understood the mechanism or not, the result is the same. Their approach was, in a very deep sense, more physically intelligent than ours. That is not just clever engineering, that is engineering in harmony with the physics of the situation. Whether the Romans understood why it worked is debatable. Probably not in our terms. But they certainly knew that it worked, because they kept building with it, century after century, refining the recipes, adapting them to local materials and local conditions. At every site, the composition is slightly different, tuned to the available aggregates and the intended purpose. That is not sloppiness, that is sophistication. They were practical scientists operating without theory, guided entirely by observation and accumulated craft. They discovered an atomic-level self-repair mechanism through empirical wisdom, long before anyone knew what an atom was. So what do we do with all this? Let me first point out something poetic about the chemistry, because it is the kind of thing that delights me. Limestone is calcium carbonate. You heat it up, drive off the carbon dioxide, and get calcium oxide, quicklime. Mix the quicklime with water, you get calcium hydroxide. That calcium hydroxide reacts with volcanic ash to make the strong matrix. Then, when a crack forms and water gets in, the lime clasts dissolve and the calcium meets carbon dioxide from the air. And what does it form? Calcium carbonate, limestone, the very thing you started with. It is a circle. The lime cycle, chemists call it. The material begins as limestone, gets transformed by heat and water and volcanic ash into something extraordinary, serves as concrete for 2,000 years. And when it heals its own cracks, it turns back into limestone. The beginning becomes the end, becomes the beginning. Nature has these cycles everywhere if you know where to look. Water evaporates from the ocean, falls as rain, runs back to the ocean. Carbon dioxide is breathed out by animals, absorbed by plants, and released again when the plants decay. And calcium carbonate breaks down in fire, does its work as concrete, and quietly reassembles itself from water and air. There is a kind of elegance there that you could not design better if you tried. Now, the practical question. Modern concrete production accounts for roughly 8% of global carbon dioxide emissions. 8%, that is enormous. Every ton of Portland cement releases nearly a ton of carbon dioxide, partly from the fuel needed for the kilns, and partly from the limestone itself, releasing its stored carbon during calcination. It is a double hit on the atmosphere. We pour over 4 billion tons of concrete every year, making it the second most consumed substance on Earth after water, and most of it will need to be replaced within 50 to 70 years. That is a staggering amount of material flowing through the economy and a staggering amount of carbon flowing into the sky. If we could make concrete that lasts 500 years instead of 50, the arithmetic is simple. We would need a fraction of the production, a fraction of the carbon emissions, a fraction of the quarrying, the mining, the transport, the demolition, the waste. You do not need to invent some exotic new technology. You just need to make what we already have last longer. And the Romans showed that this is physically possible, not theoretically possible, actually demonstrated, proven over 2 millennia of real-world testing. Several groups are now working on exactly this, inspired by the Roman discovery. Some are experimenting with hot mixing techniques using quicklime. Others are using coal fly ash, which has chemical properties remarkably similar to volcanic pozzolana, as a substitute. Fly ash is a waste product from coal power plants, and there are mountains of it sitting in landfills. Using it in concrete would solve 2 problems at once: better concrete and less industrial waste. The early results are promising, and at least one startup is already producing Roman-inspired self-healing concrete for commercial use. The irony should not be lost on anyone. We spent the last 2 centuries perfecting Portland cement. We optimized it, standardized it, made it cheap and fast and uniform. We rejected any batch that had white lumps in it. We called those imperfections. And the result is a material that falls apart within a human lifetime. The Romans used a method that was violent and messy, that produced chunks and irregularities we would throw away on a modern construction site, and their buildings have outlasted every civilization that came after them. Sometimes the imperfection is the feature. Sometimes what looks like a flaw is actually the solution. You just have to look closely enough to see it. Let me leave you with this thought, because it is the one that stays with me, the one I keep turning over. The Pantheon Dome is sitting in Rome right now. It has been raining on that dome since the year 128. Every raindrop that lands on it seeps into the tiny invisible cracks that naturally form in any concrete over time. And every raindrop that reaches a lime class triggers a microscopic chemical reaction. Calcium dissolves, it flows into the crack, it meets carbon dioxide, it crystallizes, the crack seals. This has been happening continuously, without interruption, without maintenance, for 19 centuries. The atoms in that dome are still busy, still working, still rearranging themselves into stronger configurations. The Pantheon is not finished yet. It is still becoming what it is going to be. People always ask me what physics is good for. And I say, well, it is good for understanding. You do not need to build a bridge to enjoy understanding why a bridge stands up. But every once in a while, understanding actually helps you build a better bridge, or a better dome. And sometimes the best way to build for the future is to look very carefully, very humbly at what the atoms were doing in the past. If there is one thing you take from today, let it be this. The next time it rains, think about the Pantheon. Think about 2,000 years of water meeting calcium, and new crystals growing in cracks too small to see. Think about atoms doing their work, quietly, patiently, without engineers or instructions, just following the same rules they have followed since the beginning of the universe. That is the kind of thing that makes you want to stand in the rain yourself, just to feel part of it all. Tell me, what other ancient technology do you think we have lost? Something people figured out long ago that we have completely forgotten? I would love to hear what you think.